In the last module, we talked about low-level image features and operations that we can perform on images. These are useful building blocks, but in some cases, we want to infer something more meaningful from an image. For self-driving cars, this includes geometric and semantic information about other things in the environment, such as other cars, pedestrians, road markings, signage, traffic cones, and many other things. In this video, we will define the different high-level visual perception tasks. We will then focus on the object detection task, which will be the topic of the remainder of this module. In image classification, we are given an image with an object in it, and we must correctly identify what class this image belongs to. For example, the correct class for this image would be ducky. This was the intended task for the labeled images in the famous ImageNet database, which contains over 14 million images with labels. The task is somewhat simple since there is only one object in each image and we don't need to localize it within the image. As a result, this task is not particularly useful for self-driving cars. In image segmentation is a much more challenging problem since it demands that each pixel in the input should be assigned a class. It is also a much more arduous task to provide the ground truth correct labels called annotations in this case. However, if this task can be solved, it would be incredibly useful for a self-driving car since we get very detailed information about everything that is in the field of view of the camera. A task of intermediate complexity is that of object detection. This task is more challenging than image classification since there may be many objects within one image and we should detect all of them. And because we also need to localize them with a bounding box. However, it is not as challenging as image segmentation since we don't require the same degree of precision. Nor do we worry about the classes of the pixels that are not objects. It is also significantly more straightforward to provide the annotations since we only need relatively coarse bounding boxes around all of the objects and not specific labels for each pixel. A hybrid of object detection and image segmentation is instance segmentation, where we are now tasked with finding all of the objects in the image and their exact pixel level contours. In the remainder of this module, we will focus specifically on object detection. A first question to ask before we go on is how we can even evaluate the performance of an object detector. The image classification and image segmentation tasks are relatively straightforward to evaluate since we can just look at the percentage of our predictions that were correct and try to maximize that number. In this case, we predicted 3 out of 4 duckybots correctly, therefore our accuracy is 3 over 4, or 75%. In the case of object detection, it's not so straightforward. We might detect some objects where they don't exist, we might misclassify some objects, or we might miss some completely. Let's start by reviewing the definitions of precision and recall. Let's start with just considering one object class, say duckies. In this image, we reported 3 objects, 2 duckies and 1 flamingo. The precision is defined as the percentage of the things that we reported as duckies that actually were, in this case 2 over 3, or 66%. The recall is defined as the percentage of the total number of duckies that were reported. In this case, there were 6 total duckies and we reported 2, so our recall is 2 over 6, or 1/3. The optimal ducky detector then would report all of the duckies and nothing else, and would have a precision of 1 and a recall of 1. Often there is some parameter that we can vary, such as a confidence threshold that can increase recall at the expense of precision. If we plot the precision versus recall as we vary this parameter, we will get the so-called precision recall or PR curve. This curve always starts at the top left, since precision is perfect when we detect nothing, and ends at the bottom right, since recall is perfect when we detect everything. A good objective is therefore to maximize the area under the PR curve. This is called the average precision because it averages over all the recall values. This value is hard to calculate exactly, so we can estimate it by sampling the PR curve at certain recall intervals. Typically in object detection, we sample at recall equal to 0, 0.1, 0.2, etc. up to 1.0. However, in our case, we may have many different object classes, not just duckies. As a result, we need to take the average or mean of the average precision over all the object classes. The result is the metric that is most commonly used to evaluate object detection algorithms, the mean average precision, or MAP. Another crucial consideration in the case of object detection is how accurately the bounding box is located with respect to the annotation. To evaluate this, we calculate the intersection over union, or IOU, between the predicted and ground truth bounding boxes. Here we have a duckybot with the annotated bounding box and the bounding box that the model predicted. The IOU is calculated as the ratio of the area where the bounding boxes overlap, the intersection, and the area that either of them covers, the union. A perfectly localized bounding box will have an IOU of 1. The reported MAP is always conditional on the IOU threshold. Therefore, you will hear performance of an object detector reported as, for example, having an MAP of 0.6 at an IOU threshold of 0.8. Object detection is one of the most important visual perception tasks for autonomous vehicles, and is an essential element of any self-driving perceptual stack. In the remainder of this module, we will discuss in detail how modern object detection systems work. Many of them rely on deep learning and convolutional neural networks, so we will start in the next videos by introducing some of these building blocks.